Hi everyone, my name is Nathan Mars. I'm from a company called Backtype, and I'm going to be talking about Cascalog, which is a tool we open sourced a little over a month ago. A little bit about me. I'm the tech lead at Backtype. I've been working on these many terabyte scale systems for a couple of years now. I'm working on both ETL style workflows where we take new data and try to integrate it into your output databases for consumption, and then data warehousing. So I'm going to start off with just a high-level introduction to Cascalog and some of the goals of the project. Then I hope to spend most of the presentation actually demoing the software so you can see what it's like and what it feels like. And then if we have time left, I'll talk about Cascalog and Backtype and how we use it. So Cascalog is a query language for Hadoop. It's an alternative to Pig and Hive, and the main interesting thing about Cascalog is that queries are written in a general purpose programming language called Clojure. For those of you that don't know what Clojure is a functional programming language, relatively new. It's Lisp-based, and it has first-class integration with Java. Cascalog supports all the features you expect out of a query language: inner and outer joins, aggregators, functions, subqueries, sorting. Cascalog also can read and write from arbitrary data sources. So if you want to read from HBase or Cassandra or write to them, that's not an issue at all. And if you have your own data source you want to read and write from, there's an interface such that you can do it. So you may be wondering, why did I go and build another query language when there are things like Pig and Hive out there? And the main thing is this point that Cascalog is fully integrated in a general purpose programming language, which means you have the full power of Clojure available to you at all times. And I really just cannot emphasize how awesome this is enough. It reduces so much friction from your work. For example, custom operations. Cascalog does not have a UDF interface. If you want to define a custom operation, you define a Clojure function, just like you would for other code, and you use it. Let's say you want to make dynamic queries. You want to write a function that returns a query dynamically according to some parameters. So unlike how we're accustomed to it in SQL, where you have a string and you build your string in a haphazard way, and you've got to be careful about SQL injection attacks, etc. In Cascalog, your query is a first-class entity within the language, and you can manipulate it as such. And the third point, which is something people don't really talk about, is that there's more to working on Hadoop than just querying and record processing. There's a lot of other stuff you have to do when you're working on Hadoop, such as appending data sets together and doing distributed copies, consolidating a data set. This problem that a lot of people run into where you have too many small files, you need to combine them into larger files. And then sometimes you just have other application logic that you need to execute alongside or between your queries. And because Cascalog is just ultimately Java in the end, you can use your queries side by side with this other code. Cascalog has shipped with it something called the Playground. So it's really, what this is just a data set that's served to MapReduce from in-memory. And this is what we're going to be using in my demo. And this makes it really easy to just download Cascalog and experiment with it. It literally takes 5 minutes to set up Hadoop Clojure and Cascalog locally. You just have to see the README for the project. Cool, so let me demo the software. So let me show you the data sets we're going to be querying. This is just a file within, you all see that? Need to be bigger? No? Okay. So this is the playground, and here we just have a bunch of data defined. So here we're defining the person data set, and it just contains one tuples, where each tuple contains one field, which is the person's name. Here's the age data set, which contains two tuples, where the first field is the person's name, and the second field is the person's age. Gender, similarly, two tuples. Location is four tuples of person, country, state, and city, with null values if necessary, etc. We have follows relationships, which we'll be using as well. This is kind of like Twitter follows. So let's write our first Cascalog query.
have the wireless sound.
Okay, so this will be my, so here's the first Cascalog query I'll write. I'm just going to put it down.
You actually can do Cascalog with one hand, that's what it's
Okay, so you're watching a Cascalog query run. So let me show you the query I ran. So here's a query I ran. And what this query says is this question mark arrow thing says, do a query, put the results in standard output, and I'm looking for P, so people P, for which the age of P is 25. Okay, and if we look back at our age data set, right, we bound that P value to the first field of the tuple, and then we stuck in the constant 25 in the second field. Okay, and obviously, and as you can see here, the only people who match that constraint are David and Emily, and those are the results we got. Okay, so now let's say we want to, let's say we want to do a range query. We want to determine all people who are less than 30 years old. Okay, so here we, instead of putting a constant for the age field, now we bind it to the variable A, and now we add another constraint where we say A is less than 30. We run that, right, and this gives us a different set of people. Let's say we want to know what those people's ages are. All we would do is in this, this is a vector here in the beginning. This just declares what we want as output. We just add A there as output, and we run it, and now we have the people and their ages as results. Okay, so now let's do another query. Let's determine all the male people that Emily follows. Okay, so I just said Emily follows P, and P is male. We run it, and we get some people. So the interesting thing about this query here is that there's actually a join happening here. Okay, and the join is implicit based on how we named our variables. Okay, and the reason there's a join is because follows and gender are separate data sets. Right, so gender is one data set and follows is one data set. But due to how we constrain the variables in the query, Cascalog realizes there's separate data sets and uses a join to resolve it. Cool, so let me talk a little bit more about the structure of the query. Just explain more about what is it that I'm typing, what does this stuff mean? Okay, so let's look at this query here. So we start off with this question mark arrow thing. So with this is actually kind of a convenience operator. What this does is it both defines and runs a query. Okay, you can also just define a query and not run it, and that's just like defining a subquery that you can use elsewhere, and we'll see that later on. Next, we have this standard out thing, and what this does is it creates something called a tap. This comes straight from cascading, for those of you that are familiar with cascading. In this case, this is just declaring where do we want the data outputted. In this case, it's going to output standard output. If we want to output to a text file on HDFS, we would say HFS text line, and then give it a path. So /temp/results. Okay? And now instead of printing the standard output, it'll output to the path /temp/results in just normal Hadoop format. So next we have these variables that are within square brackets. And this is just a vector of output fields. So in this case, we're interested in variables P, A, and G. So it doesn't know what P, A, and G are. P, A, and G will be constrained by the constraints that follow this vector. Notice that all variables in Cascalog are prefixed with a question mark. And we'll see a little bit more kind of the cool stuff you can do with that a little bit later on. So then following this vector, we just have a list of what are called predicates. Predicates serve to constrain the variables that you're interested in. There's a few different kinds of predicates. One are called generators. So generators are a predicate that produce data. So for example, here, age and gender are predicates because they are a source of tuples. Right, age is just defined as this set of tuples, gender is defined as this set of tuples. Another kind of predicate is a function. A function takes a variable, does an operation to it, and finds the result to one or more variables. So here, for example, here's the times, where we have times 2a. This is the time, we're just using multiplication. A multiplication function is actually a closure built-in function that we're using. In this case, we're saying multiply 2 by the variable a, and then we have this keyword here, which is the colon angle bracket, and it just separates the input fields from the output fields. This says the input is 2, the constant 2, and a, and the output is one field called a2. If a function outputs multiple fields, then you can just put another variable here, and it'll figure it out. This last one we have here, we're using greater than, this is just a filter, so this is saying only keep A2 for which A2 is greater than 50. Pretty soon we'll look at Cascalog says aggregators, which is another kind of predicate. So some of the interesting stuff happening here. So you notice how for fields I've been using either variables or constants. Cascalog's pretty smart in terms of constants. You can use a constant anywhere you use a variable. If you use it in the input, it just becomes the input of the function. If you use a constant in the output of a function or a generator, then it acts as a constraint. So here, if I were to put replace A2 with 30, this will only keep variables, only keep values of A, which when multiplied by 2 equals 30. So it's a constraint on the variable. Cool. So it's kind of to show you kind of an interesting query. So let me show you kind of an interesting query. Okay, so this query is taking, it's reading from this integer data set. So integer is just one tuples with one field, which is a number. And it's asking for all n, which are an integer, and when multiplied by itself, equals itself. Okay, and we run this, and you get what you expect, 0 and 1. So now if I want to determine all n, which when multiplied by themselves twice, I can just add it again as an input field. Functions, being just regular closure functions, can have variable numbers arguments. And I run this, and I get -1, 0, and 1. Exactly what I expect. So Cascalog behind the scenes is seeing that I'm rebinding the same variable, and because I'm rebinding it, it inserts this equality constraint, that the input of that function has to be the same as the output. Cool, so kind of, so let's just show another interesting query. So this query, we're determining all the follows relationships where someone is following someone younger than them. Okay, so we take P1 follows P2, P1's age is A1, P2's age is A2, and A2 is less than A1. Okay? This query is doing 2 joins and then a filter after the joins. But as you can see, the joins are just implicit based on the variables. And we run that, and those are the results. If we want to actually print out the actual age difference, so here all I did is I use subtraction to find the difference to the variable d, and then we just include it in the output. Okay, so let me show you an aggregator. So let's say we want to determine the number of people in our data set who are less than 30 years old. Okay, so what we're saying here is that we're interested in a variable c. Okay, and the way we're going to determine c is we're going to take everybody's ages. Notice here that I put an underscore instead of a variable for the age. Underscore just means ignore the variable. So on age is a, we're going to keep only ages that are less than 30, and then we have this c/count aggregator. Right, and what this says is just count all the tuples that match the constraints so far. Okay, and we run that, and we get 5 as a result. So let me show you another use of aggregators. Let's determine the number of people each person follows. Okay, so here, we want to know the number of people every person follows, so we say person P follows someone, and then we count into C. And so what Cascalog sees is that because P is an output variable of this query, it's going to partition the data set by P and aggregate within each partition. All right, we run that and we get the follows counts. Cool. So let me show you one more interesting query. I'll see if I can just wing it. Let's determine the average age of each person in each country in a data set. So by now I hope you can read that. We're just taking everyone's location, we're getting those people's ages, we're summing those ages into the variable s, we're counting those ages into the variable c, and then we divide s by c to get the average. And I run that, and it works. Nope. And that's the average. So kind of interesting thing about this query is that we're actually doing multiple aggregations. So Cascalog is smart enough to just bundle those aggregations into just one reducer and just do them at the same time. Another note on Cascalog's aggregators, it is doing combiner-like functionality where it does as much aggregation in the map task as possible. So these queries are actually rather efficient, even though there's only a small number of countries. So let's look at a first example of a custom operation. So we're talking about one of the advantages of Cascalog is that you write custom operations, or you just do everything in Clojure. Let's actually see what word count looks like in Cascalog, the prototypical MapReduce example. So to do word count, we're going to define a custom operation to split a sentence into its constituent words. Okay, and that's what the function looks like. It's not important to understand what this is. This is Clojure. Basically, we're defining an operation called split. It's defined as a map-cat operation. That just means the operation returns 0 to essentially many tuples. It takes in a sentence and it splits the sentence into words. Okay, so now let's look at word count. And what we're going to do is we're actually going to do word count on the Gettysburg Address. So I have the Gettysburg Address here, just split into many tuples. Each tuple contains one line. Let me write it out. Cool, so we take the sentence S, we split S into words W, and then we count. Okay, there you go, that was word count. Right, if we want to do the same query again, but we're only interested in the words that appear more than 3 times. Cool, so these are the words that appear just more than 3 times. So much more, I'm running out of time, so I'm going to skip to just show you an example of outer joins, because Cascalog's outer joins are something you've probably never really seen before. So I've shown you many examples of inner joins. Right, so this is an inner join. We're just getting every person's age and gender. So we're joining the age data set and the gender set. Right? And the thing about this query is that it's only going to give you results for people that have both an age and a gender. So let me show you how we can get null values for people that don't have an age or a gender. So what I did here is I just changed those question mark variables to double exclamation point variables. And what the double exclamation point does is it changes the meaning of the predicate it's in. So take age P, the double exclamation point A. What this says is that A will be equal to the age of P if P is in the age data set, otherwise it's going to be null. Right? And because I did it for both age and gender, this is going to cause a full outer join. Right? And then we get null values for people that don't have age or gender. So I'm just going to skip the rest of the presentation. But I think that should have gotten you a pretty good feel for Cascalog, and how it has kind of a different take on things than these other technologies like Pig and Hive. The project is posted on GitHub. I've written some introductory tutorials, which use many of the examples I used here. So you can check those out on my blog, and follow me on Twitter for updates. Can I answer any questions?
Where is code executed? For example, when using multiplication in the query, where is this get executed? In the cluster, or where you running the query?
So here I was just running, I was running actually all the queries as MapReduce, which is on my local machine. Yeah, if you were to run that on a cluster, it would run as MapReduce, yeah.
So it will be converted into the MapReduce class and
Yeah.
run in the class.
Yeah, so the conversion process is Cascalog to Clojure to cascading, which is a pretty popular framework, and then cascading goes to MapReduce.
Support for custom input formats?
Yeah, so, yeah, great support. It actually just uses cascading as tap abstraction. So you actually have, you can just plug in a custom input format. It also gives you cool things like, it gives you like an event life cycle. So like your output taps can also trigger code when like MapReduce job's complete and stuff like that.
Can you output a variable that you use in another query, or you have to output that file query again?
Yeah, so yeah, you can have subqueries. So I just kind of ran out of time. I can show you that later, but yeah, you could like,
You know, when
yeah.
you don't want to define it,
Yeah.
it's one query.
yeah, it's very, very flexible. Okay, I'll show an example. I got to go ahead. So the query I'll show is we're going to get all the follows relationships where each person in turn follows more than 2 people. Okay, so first I'm going to define a subquery called many follows. So let me just write it out. Okay, so this query, this let thing is just regular Clojure code. We're just defining a local variable called many follows, and then we're defining a subquery. So here we have this arrow operator without the question mark. So this just says this query gets all people P, for which P follows more than 2 people. And then we have our actual query here, where we get pairs P and P2, where P and P2 follow more than 2 people using our subquery, and then they in turn follow each other. and it runs. Yeah, so that was the software.
What license are you using? What license?
It's licensed under GPL.
In this system, you can omit the first condition in the inner query.
Sorry, can you repeat that?
So since P is following P2, you can omit the first condition in the inner query. Because P by default would satisfy many follows.
By itself, it's
Right. Since P is following P2, P already satisfies many follows.
what many follows is more than 2 people.
Right, but P2 satisfies many follows. So if P follows P2, then P of course P.
Well, P would have to follow at least one other person, or at least 2 other people. We can talk about it offline. Go ahead.
Any tool to manage a large set of queries that you
How do I manage it?
in case you have a lot of
Yeah.
queries.
So yeah, so the great thing is how do you manage large amounts of code, right? You can manage this exact same way. So I generally have different modules for different classes of queries I run. I have lots of like sub-queries defined on like common functions. I mean, you just use closure as a normal function in the module system.
So what's the significance of the question mark? You said you want to say something about the variables being preceded by question marks. What's the purpose?
Oh yeah, so the question mark kind of defines just kind of 3 kinds of variables. So question mark says when this variable is binded, it cannot be null, right? So it'll filter out any tuples where it's null. If you have just 1 exclamation point, then it can be null. If you have the 2 exclamation points, then it's this. It triggers those outer joins that I showed. I think we're out of time.